So like I mentioned earlier, there is not a standard cookie cutter approach to scaling up a quantum network. But there are key enabling technologies that really allow us to scale. So I'd like to spend some time kind of going over those enabling technologies. So I'll start with the quantum repeater, and that's a key component in enabling quantum networks at scale. So the primary function of a quantum repeater is to conduct an operation that's called entanglement swapping. And all this does essentially is really extending the physical distance of my entangled particles. Okay, so in this example here on the right, we'll start with an entanglement between Alice and a memory module in the repeater. And similarly, we'll have Bob entangled with another memory module at the repeater. Once we have those, we can emit those entangled photons to Bell State Measurement Station to do this entanglement swapping operation. And essentially what that does is extend the distance of the entanglement such that now Alice and Bob are directly entangled. Quantum routers are essentially quantum repeaters with more interfaces, so they can enable more complex topologies and potentially multipartite entanglement. So instead of just entangling Alice and Bob, you have the ability to entangle Alice, Bob, and Charlie. So quantum routers will play a key role in the evolution of quantum networks. Of course, as we scale up, we're going to need longer distance links. And so to really take advantage of these longer distances and to maintain as high of a generation rate and fidelity as we can, there's this technology called multiplexing. This has been done in classical networking. But essentially the idea is, in a quantum network, we have many different signals traversing the network. We have quantum states encoded in single photons, or potentially a higher dimensional state in a few photons. We also have classical signals traversing the network for communicating messages and measurement results, classical data. So we have all these signals traversing the network, and we have a channel. So can these signals coexist on the same channel? And there are different ways of doing this kind of multiplexing of the quantum data and the classical data. So this will play a key role in, as we scale to longer distances and traverse longer links, multiplexing will play a key part. When we're talking about very long distances, free space optics will play a key role as well. For example, using satellites or laser telescopes. So in this little diagram on the right, you can see we have a satellite that is communicating to a series of ground stations, which are geographically very far apart. So a free space optical channel will be more beneficial for cases where the loss in the noise is a lot easier to handle with a free space channel than having a series of repeaters, on the terrestrial link in fiber. So for supporting those really long distances, we're going to need some free space optics. Of course, the better and better our components are in the network, the better distances and performance we can achieve. So having higher efficiency photon sources and photon detectors will enable us to, on average, make sure our photon gets across the channel and where it needs to get, and we can detect the arrival with more efficiency. So better components enable better distances. This holds true for quantum memories and also light matter interfaces. So these are components that we're going to need in a full-scale quantum network. The longer we can store quantum states and retrieve them, the more efficiently we can do that. The more buffer size we have, the more things we can store. That enables longer and longer distances as well. From the software perspective, having optimized protocols with quantum protocols and classical messaging protocols enable better rates, better fidelities, and longer distances and higher connectivity. These protocols govern the behavior of all these nodes and what they're doing and how we manage the resources in the network. So making sure our protocols are optimized and we're using the resources in an optimal manner will enable, again, these higher rates and fidelities and distances. So post-quantum cryptography is an interesting one as well for enabling scale. PQC is a purely classical technology, so it is a new kind of math-based cryptographic solution that has the potential to act as sort of a gateway between distant local area quantum networks. So we can use PQC to actually aid in some of the communications where the distances are just too large to achieve with traditional entanglement. So these are some of the enabling technologies, both from the hardware side and software side that we expect to see in these full-scale deployment networks.